Hi everyone, welcome back to the channel. Today we are discussing about the boost converter, specifically focusing on a crucial aspect that often overlooked, the capacitor selection. Choosing the wrong capacitor can lead to instability, excessive ripple, and even damage your circuit. So stick around because we are going to demystify the capacitor derating and show you how to pick the perfect capacitor for your boost converter project. We have covered most of the part selection for our simple boost converter circuit, but now we need to select the input and output capacitor. For the most modern boost converter, we'll be using the ceramic capacitor, specifically class 2 multi-layer ceramic capacitor or MLCCs because they are small and have low ESR and generally great for higher frequencies. However, derating need to be considered. What is derating? It means that the actual capacitance you get from the MLCC is often significantly lower than the value printed on the package. It happens due to the factor like DC bias and the temperature. Let's say you pick 10 microfarad 10 volt capacitor for your input voltage, the 5 volt. You might think you have 10 microfarad, but when the 5 volt is applied, you could considerably less. So that Murata SimSurfing is particularly useful tool for addressing these challenges. It's a free online resources that let's see how different capacitor performs under real world. Here I have selected 10 microfarad with 10 volt with the temperature coefficient of X7R capacitor and look at this at 5 volt DC bias capacitor drops around 5 microfarad. That's the half of the rated value. And also we see that the temperature change from 0 to 80 degree also changes the capacitance. This is incredibly important to factor into your design. Now you must thinking, should I use tantalum or electrical capacitor instead of this? Well, those have their uses for most high frequency boost converters. Here we have to use the low ESR capacitor other than electrolytic or tantalum. Always pay close attention to the data sheet. Look for the ESR and ESL, the dielectric type X7R or X5R EDC, and how the capacitance changes with the temperature and the DC bias. And also check the maximum capacitance available for different packages and sizes. The manufacturer data sheet provides the crucial guidance for the optimal performance. It is imperative to follow them. For internally compensated controllers, AP3012 we are using here. There is a often relationship between the inductor L1 and the output capacitor C2 values. In the typical application, recommended to 10 microhenry inductor and 1 microfarad output capacitor. The key is that the product of L1 and the Cout remains relatively constant. So if we need to increase the L1, we would likely need to decrease the output capacitance and vice versa. For your input capacitance, remember that we could consider ceramic capacitor with the low ESR value able to handle the peak current drawn by the converter. In the datasheet is the best friend here. For output capacitor, good rule of thumb is more capacitance equal less output ripple voltage. But careful, too much or too little capacitance can cause a stability problem. If the datasheet doesn't mention peak value, you can estimate minimum output capacitance using this formula, which is Cout minimum is equal to I out into duty cycle divided by switching frequency into ripple voltage. In the current application, we are consider output current as 100 milliamps and duty cycle as 65% and switching frequency is 1.5 megahertz and ripple voltage will be 10 millivolt. By plugging this value into our formula, we will get approximate 4.33 microfarad as a minimum output capacitor and approximately we can consider 5 microfarad capacitor. If we allow the more ripple, say 50 millivolt, the minimum capacitance drops to under 1 microfarad. I hope that by considering all this scenario, we are able to calculate the input capacitors value and output capacitance value by considering the datasheet recommendation, or if there is no datasheet recommendation, by using the formula we can estimate the output capacitor. So we have covered all component parameters and how to calculate and how to consider from the datasheet and how to sizing them. So hopefully you are able to design the basic boost converter circuit. If you need any further information, I request you to fill the comment below. Thank you. Thank you for the watching.